Alright, in this video we are going to talk about exact differential equations. So first of all, let's take a look at a definition. So a first order differential equation of the form mxy dx plus nxy dy equal to 0. This differential equation is said to be exact if there exists a function f such that the total derivative of f is equal to mxy dx plus nxy dy. I know that some of you already forgot the definition of dfxy. So let's take a step back and recall this notation. So this notation dfxy, this is called total derivative of f. And by definition that we learned in chapter 4, this thing is equal to partial derivative of f with respect to x dx plus partial derivative of f with respect to y dy. So this is the definition of total derivative in the differential form. Well, we're going to use this thing later. So now let's come back to exact differential equation. So because the definition is so abstract here, so I will show you an example. So let's think this way. So suppose that we have a differential equation xy dx plus xy squared dy equal to 0. This is indeed a differential equation in the form m dx plus n dy. So we say that this differential equation is exact if I can find a function f such that the total derivative of f is equal to xy dx plus xy squared dy. Well, the main question is, does a function f exist? Right? That is the main question for exact differential equation. Sometimes you can find such a function f that fit into the equation that I highlight in yellow here. Well, in that case, we call that the differential equation is exact. Otherwise, we say that the differential equation is not exact. So now you may have a question that, how do I know that such a function f exists? So don't be panicked now. Later in this chapter, we will have more tools to check the exactness of differential equation. So now, let's take a look at the last sentence of this slide. So what is good about exact differential equation? So if I know that my differential equation is exact, what happened is I am going to have the fxy equal to m dx plus n dy, because this is from the equation that I start, and then m dx plus n dy, this is equal to 0 because this is from the equation that I double star here. So at the end, you have the fxy equal to 0. Well, it's implied that fxy must be a constancy, and that is the general solution for the exact differential equation. So let's take a look at a real example. So example 8. Suppose that we want to find the solution of differential equation 2xy dx plus x squared dy. To do this, let's observe that if we have a function fxy equal to x squared times y, then the total derivative of f, well, by definition, this is f subscript x dx plus f subscript y dy, right? And then for this question, the derivative of x squared y with respect to x, this is going to be 2xy dx, then plus, so differentiate x squared y with respect to y, so you get x squared and then dy. Now, if you let mxy to be 2xy and you let nxy to be x squared, then you can see that now you find a function f such that when you compute the total derivative, it's go back to m dx plus n dy. This is indeed a definition of exact differential equation. So this differential equation is exact. Well, when we have exact differential equation, the solution is super easy because on the right hand side here, 2xy dx plus x squared dy, it is assumed to be 0 by the given equation, and that will leave you dfxy equal to 0, right? In other words, you have d of x squared y equal to 0 because here fxy equal to x squared times y. And finally, we have x squared y equal to a constant c, and this is the solution of this differential equation. The solution seems pretty easy, right? But you can see that the hardest part of this example is that how come is a function fxy equal to x squared times y? This is a key. How do I know that this function f works? This question we are lucky enough that our m and n are not complicated, so I can eyeball the function f and get it easily by inspection. However, most of the time the exact differential equation is much more complicated, and we cannot eyeball such a function f like this all the time. So we need more tools to deal with it. Okay, from the previous slide, you can see that it is not always easy to get such a function f that fits into the definition of exact differential equation. Fortunately, we have a theorem that can be used to verify the exactness of differential equation. So theorem: a differential equation of the form mxy dx plus nxy dy equal to 0. This differential equation is said to be exact if the partial derivative of m with respect to y equal to the partial derivative of n with respect to x. Hopefully you can see that this is a powerful theorem. It means that if you start from this differential equation m dx plus n dy equal to 0, you only need to check the condition m subscript y equal to n subscript x. Once you verify this thing, it's guaranteed that the differential equation is exact. Here is an idea. By the definition of total derivative, we have dfxy equal to f sub x dx plus f sub y dy, right? And by definition of exactness, so dfxy must be equal to m dx plus n dy. And from here, you can see that if you compare coefficients, fx must be equal to m and fy must be equal to n. So fx must be equal to m, and fy must be equal to n. If you differentiate one more time, well, let's do something like this. If I differentiate f sub x one more time with respect to y, so I am going to get m subscript y. And if I differentiate f sub y one more time with respect to x, so I should get n sub x. Well, because function f is continuous, so we have f sub xy equal to f sub yx. Well, that implies m subscript y equal to n subscript x. So this is the idea how we prove this theorem. And well, this is super powerful because when we do the examples, well, we can check the exactness of differential equation by just checking this condition. Alright, let's do some examples. So find the general solution of these differential equations. So first of all, I will let my mxy to be x squared plus y squared, and then I will let my nxy to be 2xy plus cosine y. Alright, well, to check that the differential equation is exact, so I'm going to compute m subscript y. So it means I'm going to differentiate this function with respect to y. So here I get 0 plus 2y. That is 2y. And then I will compute n sub x, which is the function 2xy plus cosine y. So I differentiate with respect to x. So here I get 2y plus 0, and that is 2y. From here, I can see that m sub y equal to n sub x. So this differential equation is exact. Once we know that the differential equation is exact, then the general solution of this differential equation is fxy equal to c. Now we need to find such a function f, but from the previous slide, this is what we know. We know that f sub x is always equal to m, and f sub y is always equal to n. So we're gonna use it as a starting point. So we know that if we differentiate such a function f with respect to x, we will get m. And if we differentiate such a function f with respect to y, we will get n. So let's start by looking at this thing, f sub x equal to m. So function f, you differentiate one time, you get m. So it means if I want to find a function f, that means I can integrate back function m with respect to x, right? So this is going to be, if I want just a function f, so I just need to integrate function m dx, so it will return me back my function f, right? And then I integrate this thing, which is integrate x squared plus y squared dx, and then that will give me x cubed over 3 plus xy squared and plus this is not just a constant, but you have to say that this is a function of y. This is a key. So here you need hy. This is a function of y. This is not just a constant. This is because when you set up at first, you set up f sub x equal to m. So because you differentiate with respect to x, anything in terms of y gonna be constant, right? So your constant here is a function of y. Alright, to sum up, I have fxy equal to x cubed over 3 plus xy squared plus hy. Well, once I have this function f, I can use another condition here, fy equal to n. So I'm going to differentiate this thing with respect to y and set it equal to n. So differentiate that function f with respect to y. So I get differentiate x cubed over 3, I get 0. Differentiate xy squared with respect to y. So I get 2xy. And then differentiate hy, I get h prime y. So that is equal to 2xy plus h prime y. And then this thing is f sub y, which is assumed to be the same thing as n, which is 2xy plus cosine y. So this is 2xy plus cosine y. And now, once you compare it, so you can see that h prime y equal to cosine y. And that means just hy equal to integrate cosine y dy. And this is sine y plus a constant, let's say c1. Alright, so now I have my function hy. So I'm gonna plug in h back into my function f here. And that will lead me to the answer. So fxy equal to x cubed over 3 plus xy squared plus sine y plus c1, right? Because I just substitute my hy by sine y plus c, right? And then the general solution of this differential equation is fxy equal to c. That is x cubed over 3 plus xy squared plus sine y plus c1 equal to c. But you can group the constant together. So this is just c, right? That's all. Alright, let's do another example. For example 10, find the specific solution of this differential equation where y5 equal to 0. Alright, this differential equation looks messy now, so let's simplify it. So I have 2xy over x squared plus 1 minus 2x, right? Minus 2 minus logarithm of x squared plus 1. So I change the notation y prime to dy by dx. And then after that, I multiply dx to this equation. So I am going to have 2xy over x squared plus 1 minus 2x dx minus, well, let's change it to plus. So plus logarithm of x squared plus 1 and then minus 2 and then dy equal to 0. That looks better now. Alright, so now we have a standard form of differential equation. So this is my mxy dx plus nxy dy. Alright, first let's check that this is an exact differential equation. So I'm gonna differentiate my m with respect to y, and that will give me so differentiate this term that I highlight in green with respect to y. So I have 2x over x squared plus 1, and then differentiate to negative 2x with respect to y, so I get 0. So this is 2x over x squared plus 1. And then for n, I differentiate with respect to x. So differentiate log x squared plus 1 with respect to x. So I have 1 over x squared plus 1. And by the chain rule, I have to differentiate inner function, so I get 2x. Differentiate constant, I get 0. So here I have 2x over x squared plus 1. So that means m sub y equal to n sub x. So this differential equation is exact. Alright. So now I know that this differential equation is exact. So the general solution is of the form fxy equal to c. Now we need to find f. Alright, let's do it. We know that f sub x equal to m and f sub y equal to n. So let's start by looking at the equation f sub x equal to m. So that means if you want to find f, you have to integrate mxy dx, and that is integrate where's my function m, to xy over x squared plus 1 minus 2x dx. Alright, how do I integrate this thing? So let's first look at the first piece. So I have x squared plus 1 in the denominator. So I can do, okay, pull out y first, and then I can integrate just 2x over x squared plus 1, and then I change my dx to dx squared plus 1, and that will leave me 2x and in the bottom 2, and then minus integrate 2x dx, right? Next, let me copy this thing to the next page. So copy and then paste. Alright, so this is my function f. So we will integrate this thing, so 2x cancel. So I have y times integrate 1 over x squared plus 1 d x squared plus 1. So I get log x squared plus 1, and then minus integrate 2x dx, so I get 2x squared over 2, and then plus a function of y. As before, I need a function of y here because I start from fx equal to m, so it means a function of y is a constant. So when I have a function f like this, so I need to find a function of y hy here by using another condition. So I also have f sub y equal to n. So I will use this thing to find my h. So f sub y equal to, well, we differentiate y log x squared plus 1 with respect to y. So I get log x squared plus 1. I differentiate this term with respect to y. So I get 0. And then I differentiate the term that I highlight in green with respect to y, so I get h prime y. This thing is supposed to be equal to n, which is logarithm of x squared plus 1 minus 2. So this is logarithm of x squared plus 1 minus 2 from the previous slide. This is my n. So once I compare everything, so I get h prime y equal to negative 2y. Oh, sorry, negative 2. And then I can get hy equal to integrate negative 2 dy. This is negative 2y plus a constant c1. Once I get hy here, I can just plug in back into this equation. So I get my f, right? So my fxy is going to be y times logarithm of x squared plus 1 minus, so this cancel. So I get x squared and then plus minus 2y plus c1. So this is my fxy. So the general solution is y log x squared plus 1 minus x squared minus 2y equal to c, right? Because you can group the constant c1 with c here, right? And then after that, so the initial condition is y5 equal to 0, right? Here, y5 equal to 0. Then, well, we're going to solve for a constant c by using this initial condition. So we have, well, when x equal to 5, y equal to 0. So 0 times logarithm of 5 squared plus 1 minus when x equal to 5, y equal to 0. And this is equal to c. So the constant c is equal to negative 25. Well, to sum up, the specific solution is y log x squared plus 1 minus x squared minus 2y equal to negative 25, and that is the specific solution.